with myself, Daniel, proudly hosted by Baker Baines. And today, this webinar, we're going to be speaking about the Inventor Tolerance Analysis tool that's been becoming quite popular in the 2020 release. But before we get to that, we'll probably go in and just have a look at the previous releases of Inventor as it's been transitioned from the 2019-2018.2 release, if I'm not mistaken. So without further ado, we'll start the webinar. And thank you for joining and taking the time out this morning to join us on this webinar. So the summary of the class, very quickly. The purpose of this webinar is to introduce you to the Inventor Tolerance Analysis. We look at some of the 1D tolerance analysis tool and the reports that it creates, also the stack up of parts. We'll do a little demo as well, and also the demo is based on a real life customer that's using this, and we'll do a demo and show you how it works. But before we get to the very technical bits, let's have a look at some of the concepts before that. And notice that it all begins with the fourth industry revolution, so Industry 4.0. So let's do some time travel a while back in time. So in the 18th century, the first industrial revolution started, and it was in the textile industry with the invention of the first mechanical weaving loom in 1784. And this was in a machine-based environment. So with the first industrial revolution, we know that it began in the 18th century in the UK. Following on to that was the second industrial revolution, and the second period of which started in the 20th century, which saw an avant mass of industrial production age, in which assembly line and factory principles saw the creation of products for mass consumption. At the start of the 1970s, the deployment of electronics and IT in the industry process led to optimized and automated production. So in the second industrial revolution, we see that there have been some introductions to automation. And following on to that, we know that third industrial revolution represents a continuation of the automation of the production process, which began in the second stage, with previously held human responsibilities being overtaken by machines, right? And the current area or current revolution that we're in, which is the Industry 4.0, we see over the next decade, the fourth industrial revolution will usher in an age of decentralized production, okay, which Industry 4.0 is made possible by smart objects, okay? Automation of products and processes which manage manufacturing and production via networks is quite close to us. We've seen this happening a lot. Smart cities, smartphones, smart cars. We've seen a lot of smart products being developed in the current era. So does it still look like Chinese? It's actually easing up now, right? So building the enterprise, now we know that with all these industrial revolutions, one of the biggest ones that we're going to focus on is the product intelligence side of it, which makes up Industry 4.0. And having intelligent products allow us to predict behaviors, allow us to predict the way they work and how they're going to perform. However, we've got to create these intelligent products. And it all starts up with the execution of the system, so MES system, right? Manufacturing execution system. We see that in the graph here. There's machines, there's PLCs, or SCADA units, MES, and as well as ERP, and it breaks it down into different areas of it. And if we look at it from a manufacturing point of view, we've got the machine being built there, we've got the database, we've got the production order, and we've got the actual MES systems that allow for this, and we've got the manufacturing order. So these fall up or make up this pyramid about creating smarter tools, because it all happens before it's actually created. How it's being created? Is it being created smartly? Are the processes being smart? And we know that in the age of data, we need data is very important to all of us. We know that having the single source of truth, where it's been all combined by different aspects or different environments in the manufacturing process. So it could be the design engineers, it could be quality management, manufacturing, process, planning team, simulation team, all need to feed back into the same area of data, or required to consume the same area of data, same data downstream. Now, it's about human, machine, and readable data, making sure that data can be consumed and accessed all through the workflow. So the other thing is that ideally every part manufactured is the same size, right? Every part made to fit into assembly in the same way and perform the same way, just as we designed it, right? So sometimes the question is always asked, will the parts make up the assembly, that make up the assembly always fit together? In the real world, this simply isn't the case. Materials, equipment, tooling, environment, and operator inconsistency can all lead to slight variations in size. We know that, we've seen that before, we've heard of cases before in the past. Individually, this might not be a problem, but incrementally, these variations can stack up, preventing parts from fitting into the assemblies. They become scrap parts. Now, if you go off by, depending on the tolerance or the precision that you're working with, this could be very critical to your manufacturing process. Okay. So why tolerances? Now, we all know in engineering environments, we have to have, especially mechanical, we have to have tolerance to allow for our parts to work and fit each other. So there's something called the limits and fits, and the type of fits that we're going to work with. However, this has a large role to play with when it comes to tolerance. So when you design a part, the CAD system is perfect representation of the part. In reality, when you manufacture these parts, there's slight difference in parts. As you can see it there, we've got deviations, right? That we work with. And I'm not going to go too in depth in that because, of course, we all understand that. The purpose of the tolerance is to design and to consider allowable variation, of course. If it's going to be either a shrink fit or a press fit, we've got to understand what the tolerance is going to work with, and of course, what type of deviations that we're going to work with. Also, we also need to understand how this part is going to perform or behave when it's out being used. If we move on to that, we see that variations in geometry, sometimes the variations in locating surface on a texture could be a problem in our tooling. Variation in setting up of the fixture on the machine, and of course two-way. Two-way is always a huge possibility of variations. Material as well, so in no uniformity of material properties, internal stress relaxation if the material is not being stress treated or relaxed for fatigue, and also dimensional variation in the surface. Also, sometimes we find that in our equipment that we use, there's some issues. It could be equipment, it could be operator, also environment. Okay, so these are areas of consideration for tolerances as well as for manufacturing to precision engineering. So some of the challenges in the development is that we've seen all of these. I mean, on screen you'll see that there's quite a bit of tolerancing going on in a simple shaft. For instance, there's a lot of surface textures there. There's dimensions. There's details of what needs to happen. However, if we're gonna detail all our parts to this level of detail with all of that tolerance there in that and the specific area of tolerance, it becomes a costly factor. Knowing that the higher the tolerance or the higher the precision of finish that you have to do, the cost factor goes up. So the idea here is using the tolerance analysis. Can you predict what would happen if you go with a semi-finished turn, for example? It's a lot cheaper than grinding. And what would happen with that part at that finish? So how does it help us perform better? So the tolerance analysis helps us predict the accuracy. No part is exact, the right size. Also, variations, right? Variations in size can result in components not fitting within the assembly. Variations in size can be limited using tolerances, but the more accurate the tolerance, the higher the cost of the component becomes. And finally, tolerance analysis can allow us to find the best comparison between performance and cost. This is ideally what it is assisting us to do. So let's have a look at the Inventor model-based definition and tolerancing, so GD&T. This has been around for a couple of releases now. A lot of improvements have been done as the Inventor releases progressed. So if we go into it, we'll find that what is model-based definition and tolerancing? As we can see there, it refers to a fully defined 3D model of an individual component and product assembly. The types of information can include the metadata, of course, bill of materials, tolerance dimension with the tolerance advisor, using geometric dimensioning and tolerances, okay, GD&T, including of surface finishing, hole and thread notes, as well as general notes can be incorporated. So historically, required accompanying use of 2D engineering drawings, right, to provide such details. The annotated 3D model is often sent directly to the manufacturing to create a physical part. So what this does, in a nutshell, it allows us to skip the 2D engineering drawing and go straight into the manufacturing side of it. However, we've seen that with technology improvements, there's machines capable of reading GD&T directly, which skips out the CAM part as well. Well, included, but skips out processes in CAM part. So why would we use model-based definition and tolerancing? So the model-based definition is the foundation of the digital transformation, okay, into this digital industry 4.0. Also, the 3D model becomes a single source of the truth. So there's not much deviations or different parts or copies of the single source. It's one part which has all of the information that needs to be transferred downstream. So anyone making drawings like this, is this correct? Okay. Is it only a feature of size? Okay. Or if we look at it like that, what happens if it deviates upward as well? That is correct because you're picking up the correct areas of the dimensioning. That would be incorrect because our sizes are actually going off the line that we're looking at, and you can see in the highlights of the red lines there with the 20.3 maximum dimension it can be. Also, if we look at this, it's still maintaining in the 20.3 area that we need to work in, the scope that we've got to work in. So let's have a look at this in a bit more detail. If we look at it in here, we can see that we're actually going above our max and what the max is actually looking at. So the developments of this timeline, as we've seen in 2018, the model-based definition was introduced under the Annotate tab in Inventor. Following 2018.1, some additions have been made to that, as well as in 2018.2, where you could pick faces directly. 2019 was actually a nice enhancement to that. What it did was it allows us to be a bit more visual. So we could see, based on colors, certain aspects about constraints, constraint parts, the profile that it's been constrained, or is it partially constrained or fully constrained. And in 2019.1, there's been a bit more enhancements to that, where you could have taken that into a viewer and it was viewed using the Autodesk online viewers. As we go along, we'll see the development into 2020, Inventor 2020, and what the enhancements have been done in there. So model-based definition, best practice, not ideal, because if you look at this, I'm sure this is not acceptable in any drawing office, having a model looking like that. So definitely a no-no. What is ideal is if it looks something like this, because you're giving it the correct sizing, you're giving it the correct tolerance information. Also, you're giving it the correct dimensioning and the dimensioning techniques, right? And using that. So dimensioning techniques using best practices should apply when using the model-based definitions inside of Inventor. So the tolerance solutions we're talking about today for addressing those engineering and business challenges in tolerance analysis is the Inventor Tolerance Analysis, which is embedded inside of Inventor. And it's a 1D solution that helps understand the mechanical fit and performance of the design based on tolerance dimensions. So, or dimensional tolerances. A 1D tolerance stack-up means that the distance being analyzed and all dimensions that contribute to the distance variation are acting in the same linear direction. Linear variation of the surface on either side of the stack-up direction is considered. Angular variation of the surface relative to each other are not. And sometimes the effects of the angular variation are overlooked, and the analysis is considered to be 1D. So this is just an example of a 1D analysis. Now, look at that gearbox in there. That's quite a bit of tolerances that needs to go into that. So making sure that is right allows us to ensure the best performance of that equipment. Now, if it was if the tolerances were incorrect, we could have a gear failure, we could have issues with the actual running of those gears and where it's not meant to be. So what is this 1D tolerance analysis? As we discussed, manufacturing tolerances have been significantly impact on cost and quality. Okay, using Autodesk Inventor Tolerance Analysis is designed to help Inventor users make more informed decisions while specifying manufacturing tolerances. Right? So the 1D tolerance, as we know, is embedded in there, and the 1D tolerance, as a definition we've just discussed, allows us to be a bit more efficient when we do it. Now, how has this been impacted before this amazing tool of the Inventor Tolerance Analysis? Previously, traditional engineering tools were done by Excel spreadsheets, hand calculations, and the creation of physical prototypes are commonly used to test the fit and performance of these designs. We all agree, right? However, this approach creates a disconnect between the CAD model and what the results are. So what happens when there are changes to the 2D or 3D model, right? How does that impact? Where does it get stored? How does it get updated? Software applications are great, and that's why we're going to demonstrate how this has important aspect. I mean, this is an important aspect to do these analysis in the CAD levels that we're going to be using, well, which is Inventor. So just a bit of some information here. So the requirements versus manual versus in-CAD analysis, and you can see there's multiple types of analysis. RSS, which is root sum squared analysis, you'll see that you will be, if it's manual, for example, it's just worst case scenario, right? Or if it's in CAD, you can support worst case scenario, RSS, and the generalized static result, right? Today, we're not going to be focusing on all of them, but if we have a look at some of them, you'll see that there's some areas that we can actually solve these problems. So the advantage of performing these tolerance stack-up analysis. So why is it important? Why do we invest the time in analyzing stack-up loops? It's going to increase understanding of the part functionality a lot more easier. It will help us discover and resolve problems before producing a physical prototype, as well as we can make informed decisions that are going to save us on cost. And of course, increase product performance, reduce warranty issues, and make the product more profitable. So ideally, we want to be more profitable, right? And if you look at it here, the increasing cost of machine processes, and we can all agree that just something just rough milled is not very expensive versus something which is ground, or if it's honed, or even a super left finish that you see at the end there. Now, if we go into it in a bit more detail, we'll see that fully integrated into Inventor is the Inventor Tolerance Analysis. So there's no save your part and open it into a different application. It's fully integrated. You'll see a tab on the bottom corner of the screen, bottom right corner of the screen. You'll see a Inventor Tolerance Analysis tab in there. What it does, it calculates the cumulative effects of the geometry dimension based on tolerances, right? And if we look at the entire workflow, setting up and testing and reviewing the results, users are familiar with the Inventor interface, which includes a new ribbon with the tolerance analysis panel, right? Which you see at the bottom right of the screen. It's everything you need to calculate, multiply tolerance stack-ups in the assemblies, whether they are created natively in Inventor or opened from another CAD system, so in CAD files. You'll still find advanced statistics results to help make informed decisions for manufacturing and generate detailed reports to share with manufacturing quality engineers. And let's have a look at what it does. Okay, so going back into the previous discussion of the timeline, you'll see that in 2020, the addition of the Inventor Tolerance Analysis, that's there. And if we look at the kind of the workflow of this, so how does it work? Design, you define the GD&T is defined in the design. On the engineering side of it, the information is actually the analysis information is available to you, and then in the manufacturing side that can be used. Let's have a look at the user interface. So before we jump into the interface, we'll know that it is a product design and manufacturing collection entitlement. If you go into the account, you would be able to access it under your product design and manufacturing collection. You will see Inventor Tolerance Analysis in there. Okay, and if you look at the workflow from the ribbon itself, okay, so the stack up, the report area are the two main areas that we can look at. And what it does, it creates an automatic or manual tolerance loop for us. We can insert a new feature in the stack up dimensions. We can create additional feature thicknesses for non-design materials. And we can capture and show snapshots for each stack up to be used in the report, which is very nice. And following on that, we can generate shareable HTML reports, which can be shared downstream with the team. And the reports, of course, can be reused to map tolerance schemes. And we've got the default settings to manage all of this. Okay. Now, let's look at the stackups itself. So what does the stackups do? It consumes the 3D model annotations, right? You can define a stackup using constraints and joints. You can define a stackup manually. Assembly closure, you can define the dimension loop, and of course add an offset between parts and add a new stackup. Some of the default settings that you'll find when you open it up, I thought this is really great to show because you can see a bit of what it looks like default from a default point of view. This is a model with no tolerance assigned to it, the feature in the stack up, and you can see that the default tolerance page is opened up there, and it's got some defaults there, right? So default analysis type to be shown in the results panel, as well as you can specify quality metric most commonly used for the statistical analysis. It's been done. So 3D effects and warning. So this is also something that you would you'll also see, and what it does, it actually gives us a significant visualization of when it is in range or when it's out, predicting worst case scenario in there. Okay, so there's a customer example which has been conducted by Autodesk, and I thought it's really great to show what happens and what the team at EWS do. So they've got two different types of machines. One's a static tool, one is a driven tool, right? And there's, you can see on the driven tool, there's over 15,000 different tooling equipment that's been driven there, right? That they have available, as well as in the static tool, there's it's a custom tool equipment that can be used. Now, what was the challenge for them? Was if you look at some of the single source of the truth, they needed this to be, of course, going through the whole workflow, CNC programming of parts, quality and inspection, some assemblies instruction, maintenance instruction of the tool, after sales information, online catalog, user manuals, and of course, engineering simulation. So that whole workflow needed to be adopted or needed to be taken into consideration. But this falls down back to Industry 4.0 and the single source of the truth. Having the single source, having one file that can be used in all of these facets of the manufacturing process and environment, as well as post-sale as well. So if we look at some of the tolerance analysis that was taken into consideration here, you can see in here the stack-ups on the top right-hand corner that was there, and the indication of it being in range at the bottom. So it tells us that it was in range of the desired tolerance that was required. So some of the advantage of using this model-based definition process, there was no need to prepare drawings, so there was a cost reduction. There was continuous process, okay, from a 3D model, from CAD to CAM, all right, also to quality inspection. The reduction of CAM programming times, a reduction of about 40%, okay, which associated CAM with the associated CAM system that we use, so that was really great. And also the reduction of programming times measuring machines, so also around the 40% mark when compared to manually programming. There was also quite a bit of significant error reduction, right, by avoiding the data bridge, and inventor tolerance analysis was used to achieve this in conjunction with the model-based definitions. Now, let's have a look at what this looked like from a demo point of view. Now, this is the part that you could see in the previous slide. We'll do a quick half section of this to actually have a look and see what's going on inside. And the area of focus would be just behind that, the little ring behind that, and that component in there. So if we open that up, I mean, these are all invented standard functions. What we could do is we could go in and in our annotate function or model-based definition function tool, we could go in and add the tolerance feature in here. And we've got the tolerance advisor, which can also advise us. However, we're going to go just look at the annotation and adding annotations to here. And if we look at with the tolerance advisor switched on, you can see that as we input any new dimensions or any input new sizes, you see that they also show in the little panel on the left there. So if we go into that, we're gonna go in and perhaps pick up a tolerance in here, make sure that we choose the right type. Okay, we can leave it as default, and you can see you can add that in there, right? You can switch them on or off the sketch visibility, add some dimensions. And of course, apply them or pick up the tolerance that we want to work with. And there must be some tolerance that needs to go on the side here. So we're going to add a tolerance to that. And we can pick the precision as well. And set our precision as we go along. So 0.5. So we save the part and close it, and we can go back to the main assembly again. If we go into environments, we've got you can see the tolerance analysis tool that shows up. So again, it's not a save as and open in another application. It's all embedded in Inventor. So we can create a new stack up here, and on the right hand side, you can see the tolerance analysis. The 1D stack up panel has opened up, and we go into that. We can actually pick up the faces that we want to work with and add our tolerance in that. Now the objective here is to make sure that we can pick it and the points parts font, and we pick all the areas in there. So we know that they have been added, so it shows on the stack up details on the right hand side, and we can see the stack up and the objectives of it. So we can pick the tolerance again and give it information, knowing that once we added in a tolerance, it shows us the worst case and where we are in it. So the objective, of course, is not met, as we can see at the bottom. And we go in and add the selections again. And we pick our plane, and we can see that there is a dimension that's being created in there. Pick all of these faces, redimension them. And it shows us that the dimension highlighted in red, the bottom, is the one that is an issue. It could be out. We modify that. And you can see that the worst case scenario stack up shows us from 0.3. We can go into the contributions, and we can also modify this to adjust our initial dimension tolerance size. And from 0.2 to minus to plus 0.2, you can see that we can fall. Are we falling in range or are we not? And by just editing the size, you can see that by doing some modifications to our tolerance size, it's advising us on the RSS or worst case. Okay, in this case, it's the RSS that we're looking at, and we could go in and actually modify this dimension size for that stack up. Okay, so if we look at the summary of that, we see that our objectives have been met and we are in range to work off. Now, the input the output that we're getting is based on the input we've put in, as well as the area of our range that we need to work in. So again, if that input is going to be incorrect, we might end up with results that may not be satisfactory. Okay, and what we can do is we can, of course, go create more stack ups around the corner here. And let's do one more on the side. And we add that dimension. And you can see that the dimension value there is 0.5. And on that face, we can go in and just switch some visibility off because we want to work with the part in here only. Pick up the faces that we require to be analyzed, and okay, add our dimension value. And they modify our tolerance value, and we can see that in this here, the range that we're working off, we can go to lower limit, and we're working off worst case in this scenario. And we go to RSS, change that value, and we in accordance. So we in line to having that part being correctly, the tolerance being all correct for the purpose of its use. So the RSS will be the root setup. And of course, we can do snapshots as well as we're going along. So this could be used in our report. So all the snapshots that we want is very customizable. We take a snapshot, and just by clicking generate report, the report is generated. And we could go in and save the report out. And this is what the report looks like. All the information, and these are the snapshots that we've taken. And this could be filed away or put into your vault and attach that file or in a folder for stackups or for reports, and can be accessed by all of the accessed by anyone that has access to that to see what the information was on that file itself. So that's looking at a quick demo and what it looks like. Understanding the results. Okay, so if we look at the nominal diameter over there, or maximum or minimum diameter that we can go on the tolerance itself, if we look at it on the top there, tolerance 2, right? You'll see that the 0.5 the maximum was 2 mils and the minimum was 1 mil. So if we go in, can we go and modify that to make sure it works? So this is a simple example that illustrates the stack up, right? So nominal size is the size designed. The minimum size are all the components modeled at their minimum material condition. And the question there is on the minimum, is the gap too big? Following that, the maximum, all the components modeled at their maximum material condition. And of course, we have a clash, as you can see at the bottom there. The question is, how can we work out the acceptable tolerance without increasing the price of the component? Okay, so that was the objective of the demonstration, to show you what how you could do it and still fall in line with the design criteria, as well as being efficient with the pricing of the component. Now let's talk briefly about the results and what we can expect from inventor tolerance analysis. The simple results is the worst case scenario, right? This is the results that is easiest to calculate by hand for small quantity of parts. In this case, we simply add up all of the tolerances from the components and compare them to the tolerances of the gap. Okay, we might assume that we need to tighten up tolerances, or which can lead to more expensive inspection techniques, and means that more parts being scrapped for non-conformance, right? With the worst case is a blunt instrument, it can lead us to believe that we have a problem. In all likelihood, this wouldn't happen, right? And in reality, a few components can be manufactured at extremes of the tolerance requested. In addition, it's unlikely that all the parts that have been manufactured to the worst case tolerance can be chosen to go together in an assembly. The RSS plot looks at the probability of components being manufactured close to the nominal dimensions. In this diagram, we've worked out each combination of worst case tolerance and plot them out on a graph, as you can see on screen. So if we look at the minimum material worst case as shown on the left-hand corner there, the material maximum material worst case shown on the right-hand side, and the nominal dimension that we're looking for is 50.5. So it's plus minus 0.5. Any total of within the range 50 to 51 is acceptable. As you see, most of the combinations will fall within the tolerance zone. It is more likely that our manufactured part would fall within the accumulated tolerance than not. And of course, instead of dealing with the worst case scenario, where possible combination of tolerances and statistics approach allows us to deal with most likely combinations of the tolerance that we're working with. So understanding the results and the yield defects. So two really useful plots are the DPMO and yield, right? So DPMO is a shorter word for defects per million, right? And it's a prediction of how many components will be scrapped for each million made. Now this goes in accordance with the Six Sigma methodology, right? Yield is the same figure displayed as a percentage, right? So that's what that means, right? We can use either of these reports to make a prediction of the output quality we can get for the design tolerances that we need. So in here, all manufactured parts will be slightly different in size to the nominal dimension. If you measure every part and plot it on a graph, you would end up with a plot looking something like that, okay? So the bulge in the middle represents the average dimension of the component clustered around a nominal dimension specified. The green section allows us the distribution of components that will fall within tolerance. And of course, the red section, the red section allows us distribution of components that will fall outside of the tolerance. Okay. in real life, the predictions we make are based on statistics. We don't always come true. Inventor tolerance analysis uses quality correction factor, okay, the CP or CPK, which allows you to take real results from your supply chain and adjust the predictions accordingly, right? Okay, so let's have a look at the report we just discussed, and it gives us all of the information that we've just spoken about in the report. And that's the HTML report that we can use, right? So, addressing business cases, so making parts to a lower tolerance, make cheaper parts while ensuring the fits, save money downstream on errors by analyzing 3D model, and also you can answer that question, will the parts that we make up, the parts that make up the assembly, always fit together? And don't throw it over the wall to manufacturing. You can actually fix that before it goes out, and then of course reduce prototypes and reduce scrap. So where do we find all of this? All of this, well, all of the tolerance advisor is inside of Inventor, which you will find inside of the product design and manufacturing collection, which of course makes up the heart of the product design and manufacturing collection, which is Inventor, and it's directly linked into that. You can access it via your Autodesk account. Under products and services, you'll be able to pick up in your product design and manufacturing collection, you would be able to see the Inventor tolerance analysis inside there, ready to install and ready to be worked. So that is the end of our presentation. I'm gonna open up some time for some questions. So please, if you have any questions, please feel free to message them or type them into the type box, and when you and I will get, obviously, of course, answer that. If there's any other issues or anything that you have questions afterward, please feel free to contact me or give me pop me an email or get a telephone call. My email is daniel@bakerbains.com. So it's DANEEL@bakerbains.com. Alternatively, you can give us a ring on 011 568 2060. Just gonna leave the floor open for a couple of questions, and it seems like there's no questions at the moment. So please, if you have any questions that may have come into mind after the webinar, please feel free to pop us an email or give us a telephone call, and we're more than happy to assist. Thank you very much for attending, and please look forward to we look forward to seeing you on our next webinar. Please, you have invites to the next upcoming webinars, and we really look forward to seeing you there. Well, have a great day all. Thank you very much.